Today we will discuss the entropy production due to heat flow. As we already know that entropy is not a conserved quantity like energy, which is conserved, but entropy is not a conserved quantity. One more point regarding the entropy is that for natural or spontaneous processes, and increase in entropy is observed. So we can simply say that entropy is basically produced. Entropy is produced in, suppose, in natural or these spontaneous processes. In such processes, suppose if a system consists of several parts, then the total entropy is equal to the sum of the entropies of each part. We have already discussed this while discussing the second law of thermodynamics for open and closed systems. So we are just revising here some of the pointers so that you will get some of the basic concepts first. Also, we know that the total change in entropy can be split into two parts, ds and dis. Suppose this is equation A. Here des is simply flow of entropy due to interaction. Interaction is with xt, you can see. and the DIS is simply contribution due to changes inside the system. And we also know that DES is equal to 0 for a reversible process, and DIS is greater than 0 for irreversible process. We have actually discussed these in the previous lectures, so to clarify more you can go to those previous lectures as well. Now we will consider a closed system. Consider a closed system consisting of two phases. Suppose we will represent those phases as first and phase second. But these phases are basically maintained at uniform temperatures. Uniform temperatures, suppose we will represent those temperatures as T1 for the phase 1 and T2 for the phase 2. Now we know from second law of thermodynamics that this change in entropy is equal to dq upon T. Here dq is simply heat received from the surroundings, and T is simply the temperature in Kelvins. We will represent this as equation 1. One more point you have to remember regarding this change in entropy is that ds is positive and is an intensive property. Very important point you have to remember. So applying equation 1 to we have considered two phases, phase 1 and phase 2. We will apply this equation 1 separately to each phase. Then for the whole system we can write change in entropy for the whole system will be equal to ds1 plus ds2. So this is equation 2. we now split the heat absorbed heat received, you can say, by each phase into two parts. That means we can write dq for the first phase will be equal to deq first phase plus diq first phase. And similarly, for the second phase, we will write the second q is equal to dq. That means for the second phase plus di second q, and we will name it as equation number 3. Because of the conservation of energy, which we have discussed in the previous lecture, in that case this di first q plus di second q is equal to 0. You have to remember that this is from the conservation of energy. So it is equation 4. The entropy change for the system of two phases is therefore given by this equation. Suppose we will write the change in entropy of first, we will introduce the value of dq. We will write first d1q for the whole system upon d1 will be equal to, we have separated the dq into two terms. We will introduce those two terms here. So we will write it as d1q upon d1 plus diq upon d1. This is equation 5. Similarly, the change in entropy for the second phase will be equal to d second q upon t second will be equal to, again it will be separated into two. That means d second q upon t second plus di second q upon t second. So this is equation 6. Now substituting equations these 5 and 6 into, we will introduce these values into equation 2. So in place of d1s and d second s, we can write these two equations there. So the total change in entropy for the whole system will be equal to then dE1Q upon P1 plus dE second Q upon P second, plus here you have to use the conservation of energy, that the equation number 4 basically you have to also keep in mind that diq first will plus diq second is basically equal to 0. So in that case we will write only one term in place of di, suppose first, and q, and we will take that common and we will write it as this. Simply we have here used equation 4. So it will be 1 upon P1, 1 upon P second. So this is equation 7. Here you will see the first two terms here, they basically correspond to des of equation, the equation which we have started with, which we have named as equation A. So we can compare this equation with that, and this term, this is the third term here. So this basically gives EIS, which is entropy, which is the entropy production. This DIS basically, or you can say this third term, we have compared it with equation A. So this, when we compare this equation with that, we will see that this third term is basically equal to DIS, which is simply the entropy production arising from the transfer of heat from phase second to phase first. Why this is heat transfer? It is simply because, or as a result of temperature difference. Here you will see these two, simply the temperature difference. That means simply T second minus T1 first. So DIS will be equal to, we will compare it with equation 8, equation 7. So we can simply write DIS will be equal to DI plus to Q 1 upon T1 T1 minus 1 upon T second. We will name it as equation 8. So from equation 8 we see that if the t second is greater than t first, this t second is greater than t first, it will imply dis will be greater than 0, since ti first q is also greater than 0. Now even if t1 is less than t second, this dis will still be greater than 0. Why? Because 1 upon t first minus 1 upon t second, in this case if it is greater, will be less than 0. We have taken from equation 8. Also because diq second will be less than 0. Now the entropy production can only be 0 when thermal equilibrium is established. So we will write that in terms of temperature, that means T1 will be simply equal to T second. So from equation 8 we can basically define, this is very important here, entropy production per unit time. Per unit time, this is a very important quantity, the entropy production per unit time. It is represented by a symbol sigma, and this sigma will be equal to, which is per unit time, so we will write it as dis upon time. So it can also be written as dis first q upon dt, and the rest part will be the same. Be greater than 0, so we will name it as equation 10. This equation 10 shows that it is with respect to time, so we can say rate, that the rate of entropy production, rate of entropy production, which is simply represented by sigma, is basically the product of two terms here. Here you will see the first is this part and second is this one. So this DIQ first is simply a rate of heat transfer because it involves two. And the second part is difference of the state function. That means 1 upon T1 minus 1 upon T second. Simply a difference of state functions. This value, that means the 1 upon T1 minus 1 upon T second, or you can say this difference can be considered as the macroscopic cause, or the driving force, you can say driving force for the heat transfer. Here you have to simply compare it with the equation J is equal to Lx. So it will be simply the heat transfer, so which can be considered simply as a flux, or flow, or a consequence of the driving force. Okay, thank you.